go ahead and do a question from the spring 2013 midterm 2 on technology. So as always, as I walk through the question, I'll explain how I'm parsing the information given and any decisions I'm making as I come up with my solution. So let's get to it. All right. For each of the scenarios below, write down a production function that matches the description of the firm's production technology. So what we're being asked for is a production function here. So that's our goal in each part. All right, part A. A baker uses eggs, flour, and water to produce loaves of bread L. So note that we've got our different variables all listed for us. So E, F, and W are going to be our inputs. Loaves L is going to be our output. So if I go down here, I'm thinking of L is equals to some function of E, F, and W, all right? Okay, so 1 loaf of bread requires exactly 2 eggs, 4 cups of flour, 2 cups of water. So I'm going to write that over here as 1L, right? It's going to require 2 eggs, so 2E, right? It's going to require 4 cups of flour, so 4F, and 2 cups of water, so 2W, all right? So I'm writing it over here so I don't have to go wade through that description anymore, okay? The baker cannot produce partial loaves of bread. It only has one size loaf pan, okay? So that means I'm always going to have to use this exact proportion of ingredients, right? And what I'm constrained by is whatever ingredient is in short supply. So that tells me that I need to use a min function here, right? So it's going to be a min of my eggs, my flour, and my water, but we're going to need some coefficients out in front, right? So the way I want to think of these coefficients is this production function to spit out the number of loaves. So if I look back here, it takes 2 eggs per loaf. So however many eggs I have, the number of loaves I can make is at most 1/2 the number of eggs. So that's what I'm going to put in front of E. Using that same logic, right? 4 cups of flour. So the most loaves I can bake from a certain number of cups of flour is just 1/4 that number of cups. And then the 2W, right? I'm going to put a 1/2 in front of W. And so there is my final production function. Let's move on to part B now. The tax preparation service uses accountants and computers. So those are my inputs to complete tax returns R. So R is going to be a function of A and C, my 2 inputs. All right. Every extra computer used by the service increases the number of completed tax returns by the same amount as the previous computer. Okay, so what does that mean? That tells me that the marginal product of a computer is constant. So I'm just going to keep track of that. Every extra accountant increases the number of tax returns filed, but by a smaller amount than the previous accountant did. Okay, so that is telling me that the marginal product of an accountant is going down as A goes up, right? Each additional accountant is producing less than the previous one, okay? All right, so already from this information, I know that I want no exponent on C in my equation, so I get constant marginal product of C, and I want a fractional exponent on A so that I can get diminishing marginal product of A. Now I've got one more sentence here that I have to account for. Each accountant is more productive if there are more computers. So my marginal product of accountant depends on computers. What that tells me is that I need these in the same term, right? Because when I take a derivative of this production function, if they're not in the same term, the marginal product of A is not going to depend on C, right? That C is going to disappear. So same term to match that last sentence. No exponent on C to match constant marginal product. And we'll just pick a nice fraction, 1/2, to get our diminishing marginal product of A. Okay. All right. Moving on to part C now. Everything is the same as in part B, except that each accountant's productivity does not depend on the number of computers used by the service. All right, so we can knock this part out quickly, right? Same production function in the sense that it still returns are a function of accountants and computers. Same fractional exponent on A, because that's the same as the previous part. Same constant exponent on C, because that's the same as the previous part. But now we want MPA, the marginal product of equivalence, to not depend on C. So I need them in separate terms. When I take the derivative of this function with respect to A to get the marginal product of A, that C is going to disappear. That's how each account's productivity is not going to depend on C, the number of computers. All right. And finally, part D here. A textbook publisher uses printing presses and computers to produce textbooks, T. Right, so textbooks are output. Printing presses and computers, P and C, are inputs. Okay. The marginal product of printing presses is diminishing, and the marginal product of computers is also diminishing. Right? Okay, so we've got MPP goes down as P goes up. MPC goes down as C goes up. Right? So that's just our definition of diminishing marginal product. However, the textbook publisher's technology exhibits increasing returns to scale. All right, so here we're going to take a little bit of a shortcut and remember that our Cobb-Douglas function had this special property with increasing returns to scale or decreasing returns to scale, right? It mattered whether those exponents added to more or less than 1. It was going to give us increasing returns to scale if they added to more than 1. And so what I'm going to use is a Cobb-Douglas function. So we're going to do P times C. I need to put fractional exponents on P and C to match this, right? To match my diminishing marginal product, right? So I could use 1/2, I could use 2/3, 1/3, but to get increased returns to scale, they need to add to more than 1, right? So I'm going to use 2/3 and 2/3, right? So they're still fractions. It still gives me that diminishing marginal product of computers, diminishing marginal product of printing presses. But since they're going to add to more than 1, that's going to give me my increasing returns to scale. Now there's one last piece of information here, right? If they use 8 printing presses and 1 computer, they should publish 400 textbooks. So what that means is I actually have to scale this function so that it matches that information, right? So that it matches 400 is going to be equal to alpha times 8 to the 2/3 times 1 to the 2/3, right? And so 8 to the 2/3, right? Well, 8 to the 3rd, the cube root of 8 is going to be 2. So when I square that, that's going to be 4. 1 to the 2/3 is 1. So this is 400 is equal to 4 alpha, which means that my alpha is just equal to 100. And so my final production function is then going to be T is a function of P and C, and that is equal to 100 P to the 2/3, C to the 2/3. All right, and so that's my final answer. Now, a word of caution here, I happen to choose 2/3 and 2/3 as a lucky guess here, right? They had to add to something greater than 1. Each one had to be smaller than 1 by itself. That's what had to be true, okay? It was somewhat arbitrary that I picked 2/3 and 2/3. What worked out nicely by doing that is that when I was handed these numbers 8 and 1, well, that 8 was a lot easier to work with that 2/3 than if I had chosen something like 3/4, because that would be some big messy decimal. And so 2 ways you could approach this during the exam. When you get to this spot and you see, oh wait, I've got a number being raised to my 3/4, whatever power you chose, you can take a pause and say, maybe there's an easier power for me to choose. Make my life a little bit easier here, okay? The other thing you can do is just leave things unsimplified, right? So had I chosen 3/4 as my exponent, I would just say at the end of the day, okay, alpha is equal to 400 divided by 8 to the 3/4, whatever that is. And I would just leave it as that. That's a correct answer. All right. So we are done with the question.